Good afternoon, everyone. Good afternoon, everyone. I am Chanda Devna, one of the PMRF fellows. So, in this semester, I am going to discuss and solve some questions based on this chapter, that is reagents in organic synthesis, which has been taught by Professor Subhash Chandra Pan from IIT Guwahati. So the classes has been already started. I think 2 weeks have already done. So after those classes, whatever I will try to solve some extra questions based on those topics, which will help you to get a clear view of those concepts and how to apply those solving your questions from the upcoming examinations like CSR, NET, GATE, or your semester examinations. So here I will discuss some previous year questions and some questions from some important books also, where and after solving this question you can easily attempt your assignment which has been provided by the NPTEL. So I will try to solve here some extra questions which are not been included in those assignments, so it will give a broader view of those topics. So today I will discuss about mainly oxidation. I think the classes sir has already started discussing about the oxidizing reagents using like chromium, manganese, ruthenium and all. So let's start. So first we will discuss today that is oxidation of alcohols. So from plus 2 like 11-12 basis, you know that how alcohols can be oxidized. So if there are a number of oxidation methods, so if it is a primary alcohol, then that if you add an oxidizing agent, what will happen? It will oxidize to aldehyde. Now suppose if the alcohol is a secondary alcohol, you know now that is what is primary and secondary. If your alcohol, that is the alcohol carbon, this one, if this carbon is connected to one carbon, and another is hydrogen, another two is hydrogen, then that is called primary alcohol. Now suppose your alcohol carbon is connected to two carbon bond and one hydrogen, then this is called secondary alcohol. Now if it is connected to 3 carbon atom, that is called tertiary alcohol. Okay. So suppose you are taking a primary alcohol and adding any oxidizing agent, what will happen? It will give us aldehyde. Now if you take this secondary alcohol, it will give us ketone. I hope the mechanism of oxidation has been already discussed in the classes, so I am not going into the mechanism, then it will be a shortage of time and we can't solve the questions. So in these classes we are mainly focusing on the question. If any of you have any doubt regarding the mechanisms, you can ask me, or you can when the videos will be uploaded, you can comment on that also. I will try to discuss the mechanism in the next class. I am not focusing on the mechanism much because it will take time. And now if you take a primary alcohol and undergoes a oxidation, which is like a strong oxidizing agent. If you add a strong oxidizing agent, what will happen? It will undergo the double oxidation because it is too strong. So just after formation of this aldehyde will undergo again oxidation, then it will give us acid. It will give us acid. If you add a strong oxidizing agent, what will happen? Directly from primary alcohol you will get acid. That is through a two-step mechanism where it is going to a aldehyde, and after that aldehyde is going to a acid. So this type of oxidizing agent can be two types. One is containing transition metal and another is non-transition metal. You know that we have some reagents which have some transition metals like chromium, manganese, titanium, osmium, ruthenium. All these are transition metals. So if reagents contain a transition metal, that is called transition metal containing, and if those are not containing any transition metal, like there is no such metal in your reagent, like selenium oxide or NaCl, all these are like non-transition metal reagents. So today in this class I will mainly discuss about the oxidation of alcohol using transition metal. In the next class I will try to discuss about the non-transition metal. Here today I will discuss about the reagents containing transition metal reagents containing transition metals and their applications. So first is chromium containing reagents. So the most widely employed transition metal oxidants are based on chromium 6. What is chromium 6? 6, you know that it's the oxidation state of the chromium. In this state, you know, from the basic, if we start talking about the basic, whenever a species undergo oxidation, that itself performs the oxidation of the other, and that itself undergoes reduction. So if the chromium perform a oxidation reaction, it will oxidize the other one, and it itself will get reduced. So chromium 6 is the highest oxidation state of the chromium. So when this chromium undergoes oxidation reaction, this chromium will, whatever substrate you will add it to the chromium 6, that substrate will oxidize to it in its oxidized form. Like if you are adding alcohol, it will undergo the oxidation and it will transform to aldehyde, and meanwhile the chromium 6 will be reduced to chromium 4. Usually in this type of oxidation it is always reduced by 2 oxidation number, usually reduced by 2 oxidation number. So whenever if you are using chromium 6 will oxidize the alcohol to aldehyde or acid, and that will get reduced to chromium 4. So there I have shown some of the reagents containing chromium. So here is one, that is chromic oxide H2CrO4. By using this chromic oxide, this alcohol can be oxidized. Now can you say this is 1 degree or 2 degree? Obviously this is 2 degree. This is a secondary alcohol because this is connected to 2 carbon bond. So this is a 2 degree alcohol. So after oxidation, what it will be? It will give a ketone. So it will give a ketone. So you see another example of this chromic oxide. There is an alcohol, and it is also a secondary alcohol. It will undergo oxidation to give this ketone. Now if you can have a doubt, like I have talked about, like if it is primary alcohol, it will give aldehyde. If it is a secondary alcohol, it will give a ketone. What will happen if we take tertiary alcohol? If we take a tertiary alcohol, what will happen with that? if we use tertiary alcohol and undergoes the oxidation reaction, there will be no reaction. There will be no reaction, because there is no such H which can be removed from this along with this OH to give us this oxidation. If you go into the mechanism, you will understand that at least one hydrogen is required to perform the oxidation of alcohol. At least one hydrogen is required. So if the carbon has no such hydrogen, then there won't be any oxidation reaction. So is another example of chromium containing reagent, that is CrO3, chromium trioxide. So that can oxidize the alcohol. So here only one alcohol is there. So this is a 1 degree or 2 degree. This is a primary alcohol. So this primary alcohol will be oxidized to form this aldehyde. Another reagent, one of the most used, I think some of you have already used this in your chemistry lab, because this reagent has been used from the +2 basis, I think. So this reagent also been used for oxidation of alcohol. So you have to find if there is any alcohol center is there. So this is 1 degree or 2 degree. This is a primary alcohol. So it will be oxidized to aldehyde. Okay. So from these examples you can get an idea. But there are some drawbacks of this chromium containing reagent. What is that? That is their toxicity and environmental hazards associated with this chromium type of compounds. We all know that transition metal compounds always bit hazardous, and chromium reagents are quite hazardous. So if you are using the chromium reagent and after the reaction completion and you are doing the just after purification of the product, you just excluded the product from your reaction mixture. Now you are dumping the reaction mixture. So the reaction mixture is containing the unreacted reagents, and also after the reagents also you are getting chromium 4 or chromium 2, whatever you are getting that. So all this you are dumping as a waste. So that will have an effect whenever these reactions are performing in a large scale in industrial scale, that will create a huge hazard to our environment. So there is a possible alternative, that is by using iron 6 species. So the same type of mechanism will be performed, but instead of just chromium we are taking iron 6. But as we know that iron is not, because we are everything around us is almost made of iron. But as the iron 6 species are less reactive than that of the chromium, so they are this iron 6 species are highly reactive. So and we know that due to that it can perform a clean and high yielding oxidation of allylic alcohol. But there are some disadvantages also because of this less selectivity towards secondary alcohol. These iron 6 species are usually selective to this type of primary alcohol. Like in case of chromium reagent, you can perform oxidation of secondary alcohol also, but in case of this iron 6 species, if you are using some secondary alcohol, they are less prone to oxidize by using this iron 6 species. There is another type of important reagents which is containing transition metal oxidation reagent, is manganese containing reagents. So KMnO4 you know about. I think KMnO4 is known by everyone, because in labs it is, you can say the color of the KMnO4. So it is totally purple color. KMnO4 color is purple. We are using this KMnO4 for titration reactions also sometimes. So this KMnO4 is one of the powerful oxidizing reagent, but as they are too powerful oxidizing reagent, they are less selective than chromium 6. Like if you are having any double bond in your substrate, suppose along with this So suppose you are taking this substrate which containing an alcohol, another is a carbon-carbon double bond, and if you are adding KMnO4, what will happen? It will oxidize this alcohol. Along with that, it can oxidize with this carbon-carbon double bond also, because it is highly strong oxidizing reagent. And in case of KMnO4 also, it is very difficult to stop at the aldehyde state, because as it is too much or too strong, so it can perform over oxidation, and directly from 1 degree alcohol you can get acid by using this KMnO4. So another powerful alternative of this KMnO4 is the manganese dioxide. This manganese dioxide is highly selective to benzylic and allylic alcohol. Suppose if you have this substrate, you can see this example. So this is a benzylic alcohol because adjacent there is a benzene group, so it can perform oxidation of this aldehyde. And here also this is the allylic alcohol, can perform the oxidation, and it is, so that's why it's giving aldehyde. And you know that this three-member cyclic ring are usually considered as one of the double bond because of the close overlap of this p orbital, because there is a sp3 hybridise and there is a close overlap of this p orbital. Sometimes this tricyclic ring are usually considered as a double bond. From, I think it is all discussed in the graduation. I'm not going in very deep, but if you want to know, you can ask me. I will try to explain that. So as much for now, you just try to understand that there is a very close overlap of this p orbital, sp3 orbital. Due to that, this triple bond tricyclic ring are usually considered as a double bond, and that's why this can be considered as a allylic alcohol, and that's why it can perform oxidation reaction and give us alcohol. Now suppose you have this type of substrate. You have this one, and you are adding MnO2 in that. What will happen? From now, here you can see there are two types of alcohol. So you have to perform oxidation, and you are adding one equivalent of MnO2. You are adding one equivalent, that there is no chance of oxidizing both the alcohol. Only one alcohol will be oxidized. So which one will be oxidized? Obviously this allylic one, because I have already said this MnO2 is highly selective to allylic alcohol. So this is not allylic, this was two carbon apart, but this is allylic. So that's why what will be our product? Where the allylic alcohol will be oxidized. So allylic alcohol will be oxidized, selective to allylic alcohol. Whenever you have any substrate, but MnO2 will always oxidize the allylic alcohol. So let's try to solve this one. This came in GATE 2019. I have already discussed about chromium containing oxidizing reagents and all. So if you are adding PCC, what will happen? There is only one alcohol is there, and what type of alcohol is this? This is one primary alcohol. This is a primary alcohol. So if you are adding PCC, I have already discussed simply. If you are having a primary alcohol and if you are adding a PCC in that, you will get aldehyde. create a aldehyde. Now they have added a zinc Br2. So this is can act as a Lewis acid. This can act as a Lewis acid. So what will happen? This oxygen lone pair will be given to this one, and there will be a partial positive charge on oxygen. There will be a partial positive charge on oxygen. Due to this electrophilicity of this aldehyde carbon will be enhanced, and there is no such nucleophilic reagent have been added. There is no such water or any alcohol so which can act as a nucleophile. But in your substrate there is an internal nucleophile. There is a double bond. So you know, double bond can act as a nucleophile also because of this high pi electron density. So now this double bond will attack to this aldehyde center. This is clear. Now the complication of this question, this is very simple. That will not be asked in GATE obviously, is that this will just attack here. The complication of this is, here you can see there is a CH3 group is given, and that stereochemistry of the CH3 group has been mentioned. If the stereochemistry of the CH3 group has not been mentioned, then you will just attack to this aldehyde and you will get a proton. But as the CH3 group, the stereochemistry of the CH3 group has been mentioned, so the attack to the aldehyde group will be stereoselective. So suppose now this CH3 group is where the CH3 group is placed below the plane. So if you are imagine a paper, the CH3, and we know that this type of aldehyde, as it is sp2 hybridized, this aldehyde is planar. This aldehyde is planar. So if you imagine a paper, the aldehyde is on the paper. The aldehyde is just on the paper. Just how you are drawing it on your paper, aldehyde is like that only. It is just on the paper. How you are drawing it, the aldehyde. But this CH3 is below the plane. So CH3 is below the paper. Suppose your paper has, you can see that there is something below your paper, and CH3 is attached below your paper. But now there are two attacks are possible. One is this double bond is coming from on the paper, like from above the paper, or it is coming below the paper. So as the CH3 group is already below the paper, so there is, as and CH3 is sp3 hybridized, you know, there will be, this is CH3 is actually exists like this way. This is a tetrahedral species, so it usually exists as this way. So suppose below your paper there is this type of group, there will be huge steric hindrance. So whenever this double bond wants to attack this aldehyde center, that will be a bit difficult for it to attack from the below the plane. So the attack will be specifically from the above the plane. Now if this attack is coming from the above the plane, then this OH group will be, the attack is coming means that this formation of this new carbon-carbon bond will be above the plane. So this OH will be OH will go to the below the plane. So this OH will go below the plane. Which will go below the plane, and this part will come to the above the plane. Now you have a positive center here. Now there is a generation of positive center here. So what will happen? Simple elimination reaction. This comes here. This as a keep this as our product. Okay, understood? Let's go to the next one. So there is another reagent that is called silver carbonate. That is called silver carbonate. So as like MnO2, this silver carbonate is also selective to benzylic and allylic. Selective to benzylic fields. Draw the selectivity order. Benzylic and allylic will be at the same place. Just remind it, this is similar to manganese dioxide. After that 1 degree, after that 2 degree. Okay, so here this one is allylic, this is not, which I was already discussed. So among these, which one will be oxidized? Obviously this one. So we will get this as our product. Now as this question came in GATE will not ask only the simple one single transformation. Now as there is a OH group, and OH group is a nucleophilic, so this internal nucleophile will attack to this aldehyde center. One, two, three, four, 5. And then you can have a doubt like why it is getting the H plus. So if this OH is attacking, there will be a minus H plus. So that H plus will be added to this one. So that is, I can show it like a minus H plus plus H plus. So H plus is going from the OH and going to this newly generated O minus. Now suppose if you are taking a reaction vessel, now you are taking the substrate and you are adding the reagent. So just after formation of this one, you can't remove the reagent. Reagent is still there. So as this reagent can also react with secondary alcohol, so what will happen? This will get oxidized again. It will undergo oxidation again. form this type of ester. Okay, it will undergoes oxidation, reoxidation, and because whenever that is in reaction vessel, you can't remove the reagent, right? Reagent is still there. So just after formation of the product, that will undergo further oxidation and will give us this type of ester compound. Okay, I hope it's clear. So let's go to the next question. So now we'll discuss about oxidation of carbon-carbon double bond. So oxidation of carbon-carbon double bond. So there can be three types. What is that? You can add oxygen into this along this double bond. So another probability is if you are just adding oxygen to each carbon. One possibility is this one. So this is so last one I was discussing about oxidation of alcohol. So till today we will discuss about oxidation of alcohol by using transition metals. Next class we will discuss about oxidation of alcohol by using non-transition metals. So for now we have discussed about oxidation of alcohol and we solved some question. Next classes also I will try to solve some question based on that using transition metal, and next we will discuss about by non-transition metal. Now we are discussing about oxidation of carbon-carbon double bond. We are discussing about carbon-carbon double bond. So there are three types of chances. One is you are adding oxygen to each carbon. Another is if you just add one oxygen for both the carbon, then that will be a epoxide. This is also example of oxidation. Another is if you just cleave this double bond and add one oxygen to each part. This is also an example of oxidation. So one is this dihydroxylation, second one is this epoxidation, and third one is ozonolysis. So this one is dihydroxylation, dioxylation, second one is epoxidation, and the last one is ozonolysis. Okay, so this type of oxidizing reagent can also be two types. One is transition metal containing, another is non-transition metal, which doesn't contain any transition metal. So first we will discuss about the oxidation of carbon-carbon double bond using transition metal reagents. The reagents containing transition metal. So the most widely employed transition metal oxidants are based on manganese, ruthenium and osmium. So here I have shown example from one of each. So as I have discussed earlier also that aminophil is highly oxidizing agent. So it can oxidize alcohol as well as it can oxidize carbon-carbon double bond also. So see, and that's why this is too strong that it can oxidize carbon-carbon triple bond also. Suppose if you are having this one, KMnO4 will give us 2OH. Now in this substrate we have a triple bond. So what will happen? If KMnO4 react for once, it will give alcohol to each of the carbon. This product will be formed. Now, as the KMnO4 is too oxidizing reagent, so what will happen? It will oxidize again and it will give another 2 OH. And whenever there is a 2OH in one single carbon, that is a geminal hydroxy. Whenever there is a geminal hydroxy group, like the 2 OH are connected to one single carbon, there is a high probability of removal of water. Because whenever one carbon contains 2 OH group, there is a high probability of removal of water. So what will happen? This comes here and this removed from the system, and that will, this O minus, take this H plus. Understood, right? So there is, so this will come here, this will remove, and this will take C plus. So here will be removal of minus 2H2O, 2 molecule of water, and we will give this as our product. So simple. If there is a double bond, it will undergo the dihydroxylation. If there is a triple bond, there will be a tetrahydroxylation type of thing, and after that tetrahydroxylation, it will remove water molecule and give us this keto compound. This is the same thing happened here. This is double hydroxylation, and after that we give this keto compound. The same thing can be performed by using ruthenium oxide also. That is also a very strong reagent, and the same type of reaction will perform here, and we get this diketone compound. Now, if you use osmium tetroxide, that is bit mild. If you use osmium tetroxide, what will happen? We will get this dihydroxy compound. This I think have been, most of you have been studied this one, this osmium tetroxide reagent. So for just clarity, I will try to discuss about the mechanism of this osmium tetroxide, because the mechanism is a bit difficult and it's important also. Like from these two parts, KMnO4 and ruthenium oxide, there is no much question comes in your upcoming examination, but you can see the application of this osmium tetroxide many times. There is a various variety of osmium tetroxide reaction which you can get further. In the upcoming classes also I will try to discuss about the application of this osmium tetroxide for kinetic reactions also, like that inertioselective reaction also. We have application of this osmium tetroxide in inertioselective reactions also. So due to this importance of this osmium tetroxide, I am going to discuss in a broader way about this. So osmium tetroxide reagent, so if we look into the mechanism, this osmium starts from this tetrahedral osmium compound, that is +8, and ends up at +6. Starts from +8 and it ends up to +6. As I said, usually in oxidation reaction, there is always a two-step difference. After oxidation, there will be usually a two-step difference. So the immediate product of the reaction is osmium ester. So what is happening? If you are taking this osmium tetroxide complex, this double bond will attack to this oxygen, this double bond shift to this osmium, and this oxygen will attack to another carbon of this one, form this osmate ester. In presence of water, what will happen? This undergoes a hydrolysis reaction. So this OH will attack to this osmium tetroxide and this will open. Again this OH, another molecular OH will attack to this carbon and this part will open, and we will get this dihydroxylation compound, and as a byproduct we will get this osmium 6. Now because osmium 6 is produced in the reaction and simple oxidation, and because this osmium 6 is produced, and if you have got some idea of reactions, this osmium tetroxide are very costly reagents. So one of the costliest reagent. So whenever if you are using, and as the reagent is not regenerating in the system, after just one molecule of oxidation, just like here you are adding, like just after reaction of one molecule of your substrate you are generating osmium 6. So the reaction is like just one molecule of osmium tetroxide can oxidize one molecule of your substrate. After that osmium tetroxide reactivity has been finished. So that's why we need a huge number of, we need a osmium tetroxide in equivalent amount. Like if you are adding one mole of your substrate, you need 1 mole of your osmium tetroxide, and that is a huge 1 mole of osmium tetroxide, that is a huge amount. So for that, to make this reaction cost friendly for industrial purpose and for us also in laboratory, we usually try to reoxidize this osmium 6 in the medium of the reaction. So along with this osmium tetroxide, a simple oxidation will restore the osmium to its osmium 8, and the most effective version of the reaction makes the use of osmium. So a catalytic amount of osmium 8 can be added, or a stoichiometric amount of NMO can be added. So this NMO is N-methyl morpholine N-oxide. So what will happen? This is also an oxidizing reagent. That is also an oxidizing reagent. So what will happen? After just this oxidation reaction, as our reagents is getting reduced and generating osmium 6, so this reagent will oxidize our osmium 6 back to osmium 8 and continue the reaction. Understood? So this NMO will help to reoxidize our byproduct, that is osmium 6, and it will go again to osmium 8 and it will give us our desired product. So in this way we can make this, reuse our substrate. So there are some stereochemical factor also. If you have a OH adjacent to this double bond, now suppose this OH is above the plane. Is there any role of this OH for osmium tetroxide reaction? So there will be no such, because osmium is, if you see the mechanism, osmium is like that. So there is no such group which is highly electronegative or hydrogen bond donor. So that's why it will not undergo the hydrogen bonding with this OH group. That's why it will just give a steric effect, not a hydrogen bonding effect. It will just give a steric effect. Because of that, if the OH group is above the plane, osmium will try to come from the opposite plane of this OH group. So osmium will come from the below the plane, and this dihydroxylation will perform from the below the plane, and this one will be our major product. So this is 12 and is to 1. So that is this below the plane dihydroxylation is the major product. But if you have this same substrate, and if you add an equivalent amount of TMETEL, which can, TMETEL means tetramethyl ethylene diamine. This is called TMETEL. My slides are visible. So if you have this TMEDA group is added, a substrate is added to this along with this osmium tetroxide, what will happen? One of the nitrogen will attack to osmium tetroxide. This will open. So there will be a, so now the reagent structure has been changed. The osmium tetroxide along with this oxygen atom, there is a group that is called TMEDA. Now this nitrogen has a lone pair that can perform a hydrogen bonding with this OH group. So if you, then that's why due to hydrogen bonding, if the OH group is above the plane, the product will form. The osmium tetroxide will come from the above the plane due to hydrogen bonding effect, and we will get this one as our major product. Okay, so whenever the osmium tetroxide is using singly, just an NMO is not does not have any oxidation hydrogen bonding, it's just adding just to oxidize osmium tetroxide. Just so now, if instead of NMO, if you are using TMEDA to reoxidize the osmium tetroxide, what will happen? The reagent structure will change and it will perform a hydrogen bonding, and due to this hydrogen bonding, this osmium tetroxide will try to come from the plane of this OH group, and it will give us this one as our major product. So increasing the electronegativity of the oxo ligand and favoring the hydrogen bonding of the allylic hydroxy group. This hydrogen bonding directs the hydroxylation. So if you are adding TMADA, this hydrogen bonding effect can be performed here. So let's try to solve this question. I have tried to take this question from some important books. So it may, as I am taking from this book, so there is no such options are given. So this type of question can come to your next examinations. So what will happen? So this, what is this one? You can get confused by just seeing the structure. This is just NMO. This is just NMO. Instead of writing the name, they just draw the structure. That's why like this way they will try to make the question complicated, because whenever you are in examination stage and you are seeing this as your reagent and above the arrow, you can get confused. Okay, this is a new reagent, I don't know the use of this reagent, and you get confused. So it's not like that. This is just NMO. So if you are adding NMO and osmium tetroxide, what will happen here? So if there is a, as I have said, osmium tetroxide are selective to double bond. In the previous examples you have seen, so it will oxidize this double bond. So this is the selectivity of osmium tetroxide. If you are adding KMnO4 or ruthenium oxide, it would oxidize both the double bond and triple bond. But osmium tetroxide usually act with the double bond only. Because of these reasons, if you see the mechanism, this osmium ester, if there is a triple bond, there will be a double bond here. So that intermediate won't be that much stable. So that's why it is selective to double bond. So what will be the product? this one will be our product, where this carbon-carbon triple bond will be totally unaffected. So there is a, from here you can get an idea also, like if you want to dihydroxylate such a compound and which contains a triple bond, and you want to dihydroxylate the double bond selectively, you can perform dihydroxylation by using osmium tetroxide. Now you have this one, it will also perform a dihydroxylation. Now the question is, from which plane, above or below? Because whenever you have such group in your substrate which is showing the stereo of the substrate, you have to think about the product which is showing some stereochemistry. It's simple. So as all these groups are below the plane, and there is no such T-MEDA or TMEDA has been added. So as this, so osmium tetroxide will just follow the steric effect. So as all these are below the plane, so the OH will form just above the plane. Okay, and the rest is similar. I am not drawing this. Rest part will be just similar as the substrate. So the OH will come from the above the plane. As all these are below, so the osmium tetroxide will come from the above the plane. Now I am adding KMnO4. What will happen? KMnO4 will oxidize, as I have discussed in the earlier. KMnO4 will oxidize this double bond and perform the dihydroxylation. Now the question is, it will perform from which plane? As it is already a cyclohexane, so that is showing as a 3D. We know that cyclohexane are 3D, that is not a planar structure. I think you have taught about, if you see the ball stick model also, the cyclohexane are not planar. So they are in a 3D. So where this OH will come? OH will come from above the plane. Is it from the, like OH will form in this plane or from this here? Obviously from the below, because due to this huge group there will be a huge steric hindrance at this place. Dihydroxylation will perform from the below the plane. Okay. So there is another question which came in GATE 2023. So what will be the product of this one? So the first one is Simon-Smith reaction. If no one knows about this one, I will try to discuss in upcoming classes. So for now, just know whenever this Simon-Smith reagent has been added, what there will be a, if there is a double bond, that will give us a cyclopropane. Just like epoxide, here in case just like epoxide, it will give a cyclopropane. Whenever there is a this type of reagent, this is called Simon-Smith. Simon-Smith. I will try to discuss this in the next classes. So whenever this type of reagent, it will give us a cyclopropane ring, and that can also go through a hydrogen bonding effect. This as this is zinc type of complex has been formed, that is able to form a hydrogen bonding. So from that you can get an idea, as this both the OH group is below the plane, so this will form below the plane. So if the cyclopropane is forming below the plane, there are two hydrogen. There are two hydrogen. If the cyclopropane is forming below the plane, both the hydrogen will go above the plane. So C or D, one of this will be our answer. Now this one you can get idea. This, as I have already discussed. So if there is osmium tetroxide and OH at below the plane, so there will be no such hydrogen bonding effect. So it will come from the above the plane. It will come from the above the plane. So this dihydroxylation will be performing at above the plane. So the correct product will be option C, because dihydroxylation is from the above the plane. Okay. So like this way, you for attending the competitive exam, they usually don't give us questions based on a single concept. They usually mix up two questions and give one. So you have to have some big idea about that. So about this first one, Simon-Smith, I will discuss in the next class. I hope if you are interested to know, I will try to. So the next is oxidation of carbon-carbon double bond using peroxides. So this is the last topic of today. Oxidation of carbon-carbon double bond using peroxide. So the most general reagents for conversion of alkenes to epoxides are peroxides. So if you want to generate a epoxide you know, na? If you have a double bond and you want to generate this one, the most convenient reagent is peroxide. So there are different type of peroxide reagent. One is MCPP, that is metachloroparbenzoic acid, and second is H2O2. So, but depending on the substrate, you have to choose the reagent. All reagent can't be used for all the substrate. Like if you have been taught about the reduction reactions or something, you know that LiLH4 can't be used for everything, NNPH4 can't be used for everyone. So like the similar way, MCPPA can't be used for all the double bond, H2O2 can't be used for all the double bond. Whenever there is an electron rich double bond, means there is a double bond which is connected to some group which is donating electron towards the double bond. For that type of substrate, you will use MCPPA. But whenever the double bond is electron deficient double bond, means the double bond is connected to some group which withdraw electron from the double bond. For that type of substrate, you will use hydrogen peroxide. So if you see this one, this is simple styrene. So this double bond is connected to a phenyl group, and we know that phenyl group can push electron towards it because it's high conjugation of electron. So this can be electron donating. So this is electron rich. So this is electron rich double bond. So whenever there is electron rich double bond, we want to perform epoxidation, we will use MCPP. So what will be the product of this one? Product of this one will be this. Now, if you have an electron deficient double bond, so you know this is a alpha beta unsaturated double bond because there is a conjugation with this carbonyl which can withdraw electron from the double bond. So this is electron deficient. This is the electron deficient double bond. In such cases, for this type of substrate, For this type of substrate, what we will use? This hydrogen peroxide. So what will be the product of this one? Product will be the same epoxide, but based on the substrate you have to choose the reagent. So that reaction formula, like if you are adding hydrogen peroxide to this styrene, there will be no product formation. But if you are adding NCPBA on this hard beta unsaturated ketone, there will be no such product formation. So you have to choose the substrate based on the, whenever there is electron rich double bond, you will use NCPBA, and whenever there is electron deficient double bond, you will use hydrogen peroxide. So MCPBA can, if you have a cyclohexane, this type of group, and a double bond connected to that, so MCPBA can come. So this is planar, as this is sp2 hybridized. This is above the plane, but this is, if you consider that this is a paper, this is on the paper. So this hydrogen product, this MCPBA come from the above the plane and from below the plane also. So usually the axial attacks all prefers over the equatorial in this case. So therefore this product will be major and this will be the minor one. Now suppose we have this one. What will be our product? As OH group is given and the plane has been showed here, so obviously from that one you can get an idea that there will be a role of hydrogen bonding. So you have to consider the hydrogen bonding or not. Like in case of osmium tetroxide, we are not considering the hydrogen bonding. In case of Siemens-Smith reaction, we are considering the hydrogen bonding. In case of osmium tetroxide with TMADA, we are considering the hydrogen bonding. So in case of MCPBA, if you see the structure of MCPBA, it's like that. R group is the metachlorobenzoic acid. The structure is like that. So there is a OH group which can perform hydrogen bonding with this one. So it can perform the hydrogen bonding with this one. Because of that, wherever the OH group is, the epoxide will form in that plane. It doesn't matter there is some steric hindrance in the above the plane, as the hydrogen bonding is always preferable over steric hindrance. So that's why the epoxide will form above the plane. This part will be as same. I am not drawing this. Okay. This part will be as same. Just this double bond will be undergo the epoxidation, and the importance of this product is it will be. So this question can come in your next upcoming next examination. They will give a multiple examples where they will give a epoxide just below the plane. One will be above the plane. One will be in the plane. So you have to discuss. You have to select that one. So the one question came in 2019. So they have given this product. Now they have shown that if R equal to H and you are adding this carbenzoic acid, what will happen? And if is R equal to a CO2 ET, that is if R equal to a, this is a ester group. If this is a ester group, what will happen? So if there is H, obviously, and from the questions you can get an idea that okay, this is above the plane. This is above the plane. From the questions, from the options you can get an idea that okay, this will be above the plane. Because see, in everyone that is above the plane. So this will be above the plane. So make this, there is some, they will try to make the questions tricky by this way. You have to see the answers also. So from the options you can get an idea, okay, this will be above the plane. So as this is above the plane and if it is H, so it will be OH, and OH can perform a hydrogen bonding, and whenever there is hydrogen bonding, epoxidation will perform from the plane of the OH. So OH is above the plane, hydroxylation will, epoxidation will be above the plane. So product will be among these two. Product will be among these two. Now, if there is R equal to CO2 ET, so this is the ester group, and we know ester group can't perform hydrogen bonding. Only OH can perform. So ester, as it will not perform in hydrogen bonding, so it will just give us steric. Whenever there is no question of hydrogen bonding, that will just give us steric. So if that is a steric hindrance, then the reagent will come just opposite plane of that one. So if there is R equal to this ester group, then this will try to come from the opposite plane of this one. So this one will be, so the correct option will be option B, because the reagent is coming just opposite plane of that, because this is giving a steric. Okay, understood? I hope it was simple. So this is the last question, I guess. This is the last question of today's session. I will just give 10 seconds. So whoever is watching this one, just try to think that what will be the product. As much we have discussed till now, it is based on that. Just have a this one also came in GATE 2019. So let's try. So this is a this type of reagent can act as a, this is called Gilman reagent. This is called Gilman's reagent. Gilman is the name of the scientist. So this is a Gilman's reagent. So this will give a CH3 minus as a nucleophile. For simplification, it will just, whenever there is this type of group and whatever R is there, that will give a nucleophile. So it will give a CH3 minus, and whenever there is an alpha beta unsaturated compound and you are having a nucleophile, where it will attack? Obviously at the beta carbon, because it's electron deficiency. So this will attack to this beta carbon. So this double bond will open. So what will be the product? So CH3 will be added here, and there will be a minus center, there will be negative center. Then now as a next reagent they are adding this phenyl selenium bromide. If you just consider this as a electrophile, it will give this one. Now if you are adding this H2O2, we know that H2O2 is a oxidizing reagent. H2O2 is a oxidizing reagent. So what will happen? It will undergo, and selenium is prone to oxidize. So what will happen? This will oxidize. selenium. Now if you know about elimination reaction, that is scene elimination reaction, I don't know you guys know about that, but I will try to discuss about this in the classes. Scene elimination reaction or Chugaev reaction or scene elimination reaction. So whenever this, if you just try to draw the stereochemistry of this one, I am trying to draw the stereochemistry also, like if the CH3 group is coming attacking here above the plane, so obviously the selenium will go to the below the plane. So there is a H. So there is a H which is in the same plane of this selenium. Same plane of this selenium. Because the CH3 is above the plane. Okay. The CH3 is above the plane. So there is a chance of scene elimination reaction. So this oxygen will take this H. This come here. So as our product, get. So there is a okay. So which one will be our product? This one. So option B. So there is a huge application of this type of reaction, because whenever you want to enter a CH3 group at the beta position, you can't perform nucleophilic addition here. You can't perform electrophilic addition because you want to keep the intact this double bond. So for that one, we can perform this reaction. You can see just product and substrate is just similar. Just here there is a incorporation of CH3 group. There is a incorporation of the CH3 group. Okay, so the correct option will be option B. I hope whatever question I have discussed today seemed quite interesting to you, and try to get a overview of this one. So I have discussed about the oxidation of alcohols. Then I have showed some examples from some books. Then some other, like the manganese dioxides and their examples. Then I have tried to solve the previous year question based on that. Then we discuss about oxidation of carbon-carbon double bond and some examples for transition metal reagents. And I have tried to discuss the osmium tetroxide in a broader way, and some examples and the previous year questions. And then we discuss about the epoxidation reactions and solve some questions based on that. So thank you everyone for attending my class. In the next class, I will try to discuss about the oxidation of alcohol using non-transition metal, which was remaining. Oxidation of alcohol using non-transition metal, this one, and also some other examples of transition metal and some other examples of oxidation of carbon-carbon double bond. After that, we will move to ozonolysis, which is another type, because I have already shown that double bond can be oxidized in a 3-way. So we will move to, we have already discussed this dihydroxylation, we have discussed about this epoxidation, so this ozonolysis is remaining, so we will discuss about that also. So this is remaining. Okay, so thank you everyone. We'll meet you in the next class. Have a nice day.